So this last week in class, we introduced the notion of convergence and probability. And remember, the goal for studying this topic is to apply convergence and probability to estimators. So basically, the idea is we want what's called a consistent estimator, which is an estimator that converges in probability to the true value of the parameter that we're attempting to estimate. And then we spent some time in our last class proving some inequalities, or at least studying some inequalities that will help us prove consistency results, that is, convergence and probability results. But the first inequality we didn't prove, and I said that we would save it for a video, and this is that video. So the inequality said that the probability that some function of a random variable is greater than or equal to some constant c is bounded, so it's less than or equal to the expected value of the function of the random variable over that constant. And the proof technique here will be to start with the expected value and use the law of the unconscious statistician. So start here with the expected value of the function of the random variable, and then use the law of the unconscious statistician. So we will integrate with respect to the PDF of x, not the PDF of the transformation g of x, but we'll multiply by the function of the random variable. And our goal in this proof will be actually to integrate over a few different sets. And so first I want to introduce some notation that will allow us to compute. It basically allows us to write in shorthand some, an integral that we could write out as a long sum or something like that. But it's basically just shorthand notation. So suppose that I wanted to integrate a function, and maybe the function looked something like this, and the goal actually was to integrate only regions where the function was greater than some value c. So maybe we'll call the function g of x, because that's what it will be below. And we've got some constant c on the y-axis. And maybe we only want to find the area under the curve such that the function g of x is greater than c. Well, if we extend c out a bit, we'll see that parts of the function are below c and parts are above. So what if we wanted to integrate, starting from 0 and then out to this point here, right? That's a region where the function g is above c, so maybe I'll call this x1. And then, we wanted to skip this middle region, but then start again at this x2. We could write this integral as the integral of function g of x from 0 to x1 dx, right? That would give us the area here. And then we want to skip the region between x1 and x2, and we add the integral, say, from x2 and beyond of g of x. And that would give us, this area out here. So another way to do that would be just to write the integral over a set. And the set would be the set of all x values such that when you plug in x into g, that g of x is greater than or equal to c. And that's the kind of notation that we'll use in the proof below. And now if we wanted to add in the region between x1 and x2, we could always do that. So let me move this over. We could add on to this string here, the integral, well, just from x1 to x2 of g of x. But then, in order for this equality to hold, we would then add on the integral over the set of all x such that g of x is less than c. And all of that would be equal to the integral under the curve over the whole, the whole region of x. In this case, from 0 out to infinity. So we're going to use a trick like that because it will be helpful in proving this inequality that we have down below, this inequality here. So basically, we'll take this integral and we'll split it up across a region where the function g is above c, and then a region where the function g is below c. So we'll take the integral over the set of all x such that g of x is greater than or equal to c. And so here we're integrating g of x times f of x dx. And in order for this equality to hold, we better think about the other region, all of x, where g of x is less than c. So we'll add to that the integral over the set all x where g of x is less than c. So same integrand, g of x times f of x dx. Now, since we know that PDFs are non-negative, and we're given that g of x is non-negative, this whole integrand will be non-negative. So that means that the integral here and the integral here, both of those will be positive. And if they're both positive, that means that what we have here will be greater than or equal to just one of them, right? If we dropped one of them, for example, if we dropped this integral here, then the result would be less than or equal to this whole thing. And so that's what we're going to do. We'll take just the integral over the region x such that g of x is greater than or equal to c of the integrand g of x f of x dx. And then the next thing that we'll notice is that, well, if g of x is greater than or equal to c, right, that's the region that we're looking at, then we could actually replace g of x with just c, and the result would be greater than or equal to what we have here. So we're going to take g of x and replace it with c, and that will be a legal move as long as we keep this greater than or equal to sign here. So we'll have the region all x such that g of x is greater than or equal to c, and we're integrating now over c times f of x dx. And that substitution is legal as long as we have this greater than or equal to sign here. And then the next step is, well, c is a constant. We can pull it out of the constant, and we're left with the integral on the region all x such that g of x is greater than or equal to c of just f of x dx. And it turns out that this is exactly equal to c times the probability that g of x is greater than or equal to c. And what that means is that this integral here, you have to convince yourself, this integral here is this this probability here. So it's a probability that has to do with the function of the random variable, not just not just the original random variable itself, but the function g of x. And I'm going to leave the reasoning for that as an exercise to you, but of course it has something to do with this set here, right, the region that you're integrating over. And so in class on Monday, our goal will be to start with a discussion of this video and to see if there's any piece of this proof that you have questions about, and maybe in particular how this integral here can reduce to this probability. And then of course, once you see that, right, how this integral reduces to this probability, then the proof is done, because we have the expected value of the function of the random variable is, well, there are some equalities, but then there are some greater than or equal to, so this quantity is greater than or equal to this quantity, and then of course you can divide over by the positive constant c, and you have the correct result.